In section 7, we studied likely the most general case for continuously payable annuities. In the final two sections, section 8 and section 9, we actually study two special payment functions. Remember in section 7, low t can be anything. Now we study two special cases. This is a linearly increasing function. Right? It goes from 0 is the initial point, and then it increases linearly. At time 1, the payment rate is 1. At time 2, the payment rate is 2, which somehow matches, with what we studied earlier on. But remember here, say in between, let's say at time 0.5, the payment rate would be 0.5, not 1. Although at time 1, the payment rate is 1. At the final part, what do we study is this. We study a continuous payable annuity for n years, and the rate of payment is n minus t. So at the very beginning, you have the highest payment rate, that is n, and it gradually decreases. So if I draw the graph, let's consider for n years. So this is the low t equals t. Okay, let me extend the y-axis a little. So here's n. So let me use dotted line to denote the decreasing case. So this is the decreasing case. So in section 8, we study this case. In section 9, we study the decreasing case. So both 8 and 9 are special cases of what we studied in section 7. So if you understand the setup of section 7, those two would be examples of what we studied before. Here I did give you some result, but since this is a general, since this is a special case, what we studied, so I don't want to go through this result. I directly give you example. As mentioned, this is the setup. Okay, let's directly do example, and let me convince you that formulas are not important in this course. 3.17. Let's go to that example. It would be on page 87. In this example, Sam receives continuous payments at the annual rate of 8t plus 5. From 0 to 10, the continuously compounded interest rate is 9%, so it's a constant. Determine the present value at time 0. So first of all, this is a non-standard case because for the standard case, low t should be t. So according to this, you're going to decompose this as 8 times t plus 5. Right? 5 is a level payment. This is 8 times a special case of this formula. Right? So if you're going to apply the formula, it will be 8 times this plus 5 times standard annuity, continuously payable. But I don't want to do that. I directly 3.17. So we want to know the present value. The payment goes from 0 to 10. At each time is 8t plus 5. Since this is a present value, so it's exponential of negative from the starting point is t to the current time, which is t. The starting time is 0, excuse me. The discount rate is 0.09 df dt. Okay, so let's quickly break everything. It will be t times e to negative 0.09 t dt plus 5 times from 0 to t e to negative 0.09 t dt. Okay, this part you should see the result right away. Right, it should be 5 divided by the exponential order, then it's 1 minus negative 0.9. Okay, this part requires integration by parts. Let's do a general one. From 0 to what do you want to use? Let's use b. Okay, and here we use t e to negative delta t. So I do this more general. For this particular case, you plug in 10. For B, you plug in 0.09 for delta. So let's do integration by parts. Let's move the more complicated term inside. Okay, then obviously I need to divide by this negative delta in front. Okay, then the first step is to take them out. This is from 0 to B. Then will be minus minus becomes plus. Switch the position. Okay, for this, we know it's going to be 1 over delta square, 1 minus negative delta B. Okay, and you plug in the values. Plug in B, you get negative B over delta B to delta B. Plug in 0, obviously 0. Right? If you want, you can call this somehow a formula if you want, right? Because this is rather important. It is just a calculus exercise, right? Then you plug in, you will get 8 plus 1 divided by 0.09, 1 minus negative 8 plus 5 divided by 0.9, 1 minus e of negative 0.9. Okay, the rest you can just use calculator. This is and this step is fairly easy. 3.8, 3.8. They just want the. By the way, the result is about 257.69. 3.18. They want you to calculate the accumulated value. So once you know the present value, accumulated value simply times by 0.09 accumulated by 10 years. So this is very trivial. But of course you can apply this result if you want. Okay. But given that we already solved in 3.17, you can just times by the accumulation factor to get the correct result. 3.19. So you have this payment from 2 to 7. So the continuous payment starts at time 2, ends at time 7. The payment rate is 2t minus 3. And the force of interest is 0.06%. Calculate the accumulated amount at 7 years. So again, right? So the starting point is 2, the ending point is 7. Okay, that's exactly when you are going to receive this continuous annuity. The rate is 2t minus 3. Now, because we want to know the AV at 7, so we need to actually accumulate from the current time t to time 7, 0.06 ds. So okay, there are a few things you can do. First, well, you can distribute and move this guy outside. Right, this 0.06 times 7. Well, I can put 2. Then I have from 2 to 7. What I have inside would be t times e to negative 0.06t. Okay, and then I would have another term which is minus 3. I still have exponential of 0.42 from 2 to 7. This is negative 0.06t dt. Here is dt. So the second integral is very easy to handle. The first one looks highly similar to what I did down here. But let me change this a little. Let me give you the general formula. So let me erase. I won't go from A because sometimes we have more general results. So let me erase everything. okay? Because here, we start at 2, not 0. So that's why I want to give you somehow more general result. Let's use pink again. So from A, so this is the same, right? So we plug in, here's A, here's A, okay? Then what do I do is, I can take this entire negative thing out, right? Then it will be B times negative exponential to negative delta B minus A times exponential of negative delta A, okay? And then I have negative 1 over delta square exponential of negative delta B minus exponential of negative delta A. If you want, you can switch the negative sign and put this as positive if you want. So at this step, I would leave this to you, right? Because for both integrals, they are special case, right? Here I can take what is A? A is 2, B is 7, delta is 0.06, right? So once I gave you this general results, this is rather easy. So as you can see, once you understand section 7, there is really no formula, right? But if you don't understand, your job is going to be tough because, well, this formula is not that easy to memorize, right? But as you can see from what I did, it's basically a calculus exercise, right? Writing this down, I believe at this moment it should be straightforward, right? You write an integral, okay? For this, let me get blue to highlight. So when I write the first integral, this lower point is the starting point of your annuity. This point is the ending point of your annuity. This function is the payment function. Okay? If you are calculating the present value, this would be, well, you want your present value to be evaluated. If it's time 0, it's time 0. If it's time 1, it will be 1. This 0 and this 0, they don't need to be the same because this is the starting point of your annuity. This is the ending point of your annuity. This point is when your present value is evaluated. This T is obviously the current time. So that's everything for the PV. For AV, everything the same, except now you start from what you are right now, which is small t. You go to the point when your accumulated value is computed. Okay, so this 7 and this 7, they have different meaning, although in this case they are the same. I can change this to 8 if I want. So let's say I want my present value to be computed at 8, then this 7 will be 8. But this 7 remains the same because I have not changed the period when the continuous payments are going to be received. So those two corresponds to the payment periods of your continuous annuity. This is the time at which your accumulated value should be computed. Okay. We have, oh, by the way, this is IA. For perpetuity, you never calculate future value because future value is always infinity. So again, let's use this to analyze, okay? So now I have a perpetuity which starts at time 0 and it never ends, which means there's no ending point, so it's infinity. The payment rate is T as given. So now I want to discount, so it's X. So it's exponential negative from the discount point is 0 to the current time is T delta ds. Right. So once you do this enough, you can have the calculus done in your brain because all we need to do is integration by parts. We move this to the differential. You need to divide by this, then it becomes from 0 to infinity. Minus minus becomes plus, and I need to factor out another delta. 1 minus it. Again, here it goes to infinity, right? So when I plug in infinity, it's 0. When I plug in 0, it's 0. 0 minus 0. Okay. Here, 1 minus, when I take it to infinity, I will get 0. So, right, so it's easily this result. Okay. That is, if you want to memorize it, you can, but it's a rather simple result. The next one is for continuously decreasing. The setup is basically the same, except that now the payment rate is n minus t, and usually it starts at time 0, ends at time n. So you have continuous payments, okay, from 0 to n. At 0, you have the highest rate, which is n, and then it decreases to the final time you get 0. Right? So it's decreasing. Right? I draw the picture earlier on in this lecture video. So how do we calculate present value? Integral from the beginning of this payment, which is 0, ending point of this annuity, which is n, the rate of payment, n minus t. Because I'm calculating the present value, so it will be exponential of negative. I want my PV to be evaluated at 0, so that is the meaning of 0, to the current time, delta ds dt. Okay, now please do the integral. Okay, this once you do everything, you will actually get the formula you are looking for. Here we have some examples. Let me do one of them. Let me do 3.21. We want to calculate the accumulated value. So the setup is the payment rate is 10 minus t. It goes from 0 to t for the continuous payments. The force of interest is 6%. Okay, I want to know the accumulated value at time 10. At time 10. So first, this is a continuous annuity which pays from 0 to 10 at rate 10 minus t. Since I'm calculating accumulated value, so I will do accumulation from the present time to when I want this to be calculated. 10. 0.06 ds dt. Okay. So it's 10 minus t. Here is 0.06. 10 minus t dt. Okay. Well, you can use something to replace. Let's use u to replace it. So when t is 0, u is 10. When t is 10, u is 0. Here's u, 0.6 u. dt is negative du. So you can switch the position, then cancels the negative, right? This is a standard integration by parts. I actually have the formula down here. So if you want, you can directly apply, right? So, but you can also calculate this, relatively easily, right? So once you have done this enough, you can really write down. You don't need to do everything, right? You don't need to do integration by parts. It's done automatically in your brain if you have tried this enough, right? So you have this thing, the e 0.06 times 10 minus 1, right? And then you finish, you get the result, right? Most of the time we deal with exponential function, and exponential function is likely one of the easiest to do the integral, right? So practice, and if you have trouble, you should go to your calculus textbook to bring the exercise to see how integration by parts is done. How do you do integrals for a standard power function and exponential function? Okay, I think I have done quite enough examples. If things still don't sound right to you, the best way is probably go to the calculus notes to see what you studied there and use the example there to help you understand. Because once you pass the calculus prerequisite, what we did in the last 2 or 3 videos is very straightforward, if not easy. Okay, let me end here.